1.6 is titled The Kinetic Theory of an Ideal Gas. The gas laws we've talked about so far are empirical, and we haven't really talked about why gases behave as they do. If you think back to honors class, we discussed the KMT, Kinetic Molecular Theory of Gases, and it does attempt to explain why gases behave the way they do. There are 5 postulates to the kinetic molecular theory. First of all, we know that a gas is composed of very, very small particles, and there's a lot of space in between them. So when we're comparing the size of the particles to the distance between them, we say the size is negligible and assume to be 0. Second, the gas particles are in constant random motion. Molecules, they move in a straight line in all directions and different speeds until they hit something and bounce back. The third postulate, these gas particles exert no attractive or repulsive forces on each other. This is because they're going so fast and they're so far apart that they don't care where the other one's at. They have no attractive or repulsive forces. The fourth postulate, the collisions between the particles are elastic. So when these particles collide, the kinetic energy is conserved. The last postulate says the average kinetic energy of particles of a gas is proportional to the Kelvin temperature. Now we know the kinetic energy is equal to 1/2 mv squared, where v is the velocity of an object. In this case, kinetic energy is equal to 1/2 mu squared, where u is the velocity of a particle. And this is actually proportional to temperature, and there's no proportional sign on here, and I'll have to just excuse this because I can't really write the proportion sign. It almost looks like infinity, but you get what I'm saying. The kinetic energy is directly proportional to the temperature. One of the really important features of the kinetic molecular theory is how it explains the ideal gas law. According to the KMT, this pressure that we encounter from gases is due to the countless and numerous collisions that they have on the walls of the container. So as they're hitting the walls of the container, we know kinetic energy is conserved. Some of that energy is actually transferred into the walls of the container, and we're creating that pressure against the walls of the container. So the pressure is proportional to the frequency of collisions. It's also proportional to the momentum of the collisions. Again, it shows a box instead of the proportional sign, so I drew a little box equals proportion down there. So we can say P, which is pressure, is proportional to N times U times 1/V, which is also proportional to M times U. When talking about molecular speeds, and we need to talk about diffusion and effusion. So when we're talking about molecular speeds, a very important graph to look at is the Maxwell distribution, and it is shown on the next slide. I think they want you to guess what it is here, but just look at the next slide. So molecular speeds are actually distributed, so not all the speeds are exactly the same. And as we increase the temperature, the most probable speed is going to increase, and the distribution is going to widen. So this is the graph of Maxwell's distribution of molecular speeds that I was discussing in the previous slide. As you can see, we're graphing the relative number of molecules versus the molecular speed. When the temperature is increased, the hill actually flattens out, but the distribution widens. So the average molecular speed is increasing. Since not all speeds are the same, it's really useful to be able to find a way to measure the speeds of the gas particles. We can do this by measuring the root mean square, or RMS molecular speed. This is represented by a lowercase u, and it's equal to the speed of a molecule having the average molecular kinetic energy. When we do the problem, we use this formula. U is equal to the square root of 3RT over capital M. Of course, R is going to be the gas law constant. We're going to use 8.315 joules per mole Kelvin, which of course means your temperature has to be in Kelvin, as is with all the other gas laws. And molar mass here, just make sure you have it in kilograms. When we're using these units, then our RMS speed will be in meters per second. The next 2 topics we're going to look at are diffusion and effusion. Diffusion is the transfer of gas through space or another gas over time. So if I had a helium balloon and I pop the helium balloon, of course the helium's not going to stay in the perfect shape of the balloon. It's going to diffuse into the room around us. This is very important to guys and girls who like to wear cologne or perfume. We need the scent of this cologne or perfume to diffuse throughout the room so that people can smell it. However, we don't want it to diffuse all at once. We would like the diffusion to happen over time so that we can smell good all day. Effusion is the transfer of a gas through a membrane or an orifice. If you have the normal balloons, not a Mylar balloon, but a normal rubber-like balloon, when you blow it up and you let it sit over time, whether it's filled with helium or air, over time it slowly deflates. And the reason why it slowly deflates is because there are the tiniest little pores in those balloons. And the gas is going to effuse slowly through those membranes. This is also how water gets into and out of cells. So when we're talking about the rate of effusion is going to be proportional to the inverse of the square root of the molecular mass. Basically, think about it. If something's heavy, it's going to go slow. So the heavier something is, the slower it's going to go. This picture is just a nice model of effusion. You see that there's gas on one side of the box, and in the other side it started out with a vacuum. So eventually what happens is that the gases, as they're hitting all the areas of the walls, sorry my arrow is a little screwed up there, they're hitting all the different sides, eventually they're going to hit perfectly and go through the pinhole into the other side, into the vacuum. Because as they are hitting the walls in the chamber with the gas, they're creating pressure. And since the other side doesn't have much pressure, it's going to be easier for some of those gas molecules to effuse through the hole and to the vacuum side. This is a good model of effusion. So the rate of effusion is also directly proportional to the speed, the URMS. Think about it. The faster the molecules are going, the more likely they're going to hit exactly where that hole is. So if something is moving faster, it's going to also effuse faster. There are other conditions that come into play, like the size of the pores. So calculating absolute rate of effusion takes a lot of work. But it's pretty easy to compare the rate of effusions of two gases. So in this course, we'll be looking at effusion more than diffusion, but you need to know what both are. So when we're talking about effusion, the rate is the amount of gas, either usually measured in liters or moles, per an amount of time. How much time did it take for a certain amount of gas to effuse? Thomas Graham came out in the mid-1800s and did some experiments with gases and found an experimental relationship with this, and it's actually supported by KMT. So let's take a look at Graham's law of effusion. So according to Graham's law, the rate of effusion or diffusion is inversely proportional to the square root of its molecular mass. So we can compare two different gases, gas A and gas B, but we need to know the molecular mass of at least one to find the molecular mass of the other. Or we can use the molecular masses of two gases and find the rate for either A or B. For this diffusion, rate can be either distance per time or amount of gas per time. And the time to effuse or diffuse is inversely proportional to URMS and directly proportional to the square root of molecular mass. So again, if something's moving very fast, it takes less time. Something's moving slow, it takes more time. And if it's very big, it's going to move slowly. If it's very small, it's going to move much more quickly. Go ahead and try these gas law problems. We have a Graham's law of effusion problem and also a problem to calculate the time of effusion. So give these a try, make note of any questions that you have, and we will discuss these tomorrow in class. In addition, we will also be doing some practice problems.